Assalamualaikum dan salam sejahtera. Bertemu kembali di part 2. Kita continue pembelajaran kita dalam tajuk temperature measurement. Sebelum tu kita recap, kita dah cover the principle untuk a temperature sensor. Ada 4. Kita dah talk about the material expansion, the thermal expansion. And then kita talk about apabila ada electrical resistance with a temperature, and then the principle yang ketiga adalah mengenai contact voltage between two dissimilar metal, or we call as a thermoelectric temperature measurement, or the short term we call as a thermocouple. Okay. What is a thermocouple? Thermocouple is the most common method to measure and control temperature in electrical circuit. Selalunya device yang ada capability to detect the temperature, we use a thermocouple inside the electrical part. Okay. When the two conductors of dissimilar material are joined to form a circuit. Okay. This happens when two conductors of dissimilar material are joined to form a circuit. Okay, created by welding, soldering, or by any method that provide a good electrical contact, and the output is a voltage. There is a definite relationship between the voltage and the temperature. Figure 9 shows the basic concept for the thermocouple circuit when you have your T1 junction and T2 junction, which is a dissimilar material, and you calculate for the value for the voltage, or we call as a EMF. Okay. Okay, we continue. This thermocouple circuit measure the difference between T1 and T2. If T1 and T2 are not equal, infinite open circuit electric potential EMF is measured. As I mentioned before, the EMF is measured from here, right? If the temperature T1 and T2 is a different value, so you can calculate the value for the EMF, which represent the output of the voltage of the circuit. Okay, a thermocouple junction is the source of an electronic force EMF, which give rise to the potential difference in the thermocouple circuit, or we call as a potential difference, a similar one. Three basic phenomena that can occur in a thermocouple circuit. The first one we call as a Seebeck effect. Second one is the Peltier effect, and the third one is a Thomson effect. What are the difference between that effect? So we go one by one. Okay, the Seebeck effect. The Seebeck effect is the generation of voltage potential in an open thermocouple circuit caused by a difference in temperature between the junction in the circuit. So if you can see that the Seebeck coefficient, the alpha A beta, is calculated from the changes of the EMF with respect to the dt, the temperature, the temperature difference of the circuit, and then which A and B refer to the material that comprise the thermocouple, the two dissimilar metal. Okay, and how about the Peltier effect? Okay, the Peltier effect is when a current pass through, bila ada current yang melalui, the junction change its temperature as heat observed and generated. So you can see the diagram for the Peltier effect. Due to the current flow across the junction of this metal, you have your different type of the metals here, and they have the heat transfer during the flowing of the current in the system, in the circuit, right? This effect is due to the thermodynamically reversible conversion of energy as a current flow across the junction. So how you want to calculate the heat transfer from here to maintain a constant temperature is Q pi is equal to pi AB I, when pi AB is the Peltier coefficient and I is the current flowing through the junction. It's very straightforward and you can understand that. And then the third one, sorry, this is the third one. Okay, this is the third one, the Thomson effect. Okay, what is the Thomson effect? Occur in a thermoelectric circuit. Consider the conductor shown in figures below. which subject to a longitudinal temperature gradient. So you can see the T1 and T2 is in the same longitudinal temperature gradient, and also subject to the potential difference. They have the different EMF such that there is a flow of current and heat in the conductor. Again, to maintain a constant temperature in the conductor, is found that the quantity of energy different than the joule, or we call as a I square R, must be removed from the conductor. The energy expressed term of a Thomson coefficient sigma S Q sigma is equal to sigma I different of the changes different of the temperature. So this is how the Thomson effect is about. Okay. Okay, now we go to the fundamental of the thermocouple law. Okay, they have a three law that related with the thermocouple fundamentally. The first one we refer to the law of homogeneous material. What law of homogeneous material say about? A thermoelectric current cannot be sustained in a single homogeneous material. Dia tak boleh berlaku, thermoelectric current tak boleh berlaku hanya pada single materials by the application of heat alone, regardless of how it might vary in a cross section. In other words, mesti ada intersection dissimilar contact of the material. Tak boleh homogeneous material only. Okay. The second one is a law of intermediate material. What is the law is about? The algebraic sum of the thermoelectric force in a circuit composed of any dissimilar material is zero if all of the circuit is at a uniform temperature. So the summation of all the thermoelectric force is equal for both material, for dissimilar material. At the end of that is equal to 0. And last but not least, the third law is called as law of intermediate temperature. Is said that the EMF3 is equal to EMF1 plus EMF2, or if two dissimilar homogeneous materials produce EMF1 when the junction is at T1 and T2, and produce the EMF2 when the junction is at T2 and a T3, then when the junction is at T1 and T3, so the EMF3 is calculated from the summation of the EMF1 plus EMF2 will be produced. Okay. I think you don't need to remember. You just understand. You can differentiate for every law here. What is the difference? What is the meaning of the law? It should be okay. It should be enough. Okay. Okay. We go to the basic temperature measurement with a thermocouple. So from here in the figures 2, we have a two type of the thermocouple temperature, which has a different reference junction here. If you can see, they have one and this is two reference junction. So in figures 12a, okay, here the thermocouple wire are connected directly to the potentiometer here to measure the EMF with only one reference junction. However, in the figures 12b, the copper extension, so this is the caramel and this is a constantan. The second one, they have the copper wire, copper extension wire are employed and creating a two reference junction. So what is the difference is about? What is the difference between both circuit? Okay, figures 12 show a two basic thermocouple circuit using the caramel constant copper thermocouple and the ice bath to create a reference temperature. If you can see, they use the ice bath to create the reference temperature in the circuit. Okay, and also they use a different dissimilar metal in their system. Okay. The law of intermediate material, if you still remember what is the law of intermediate material, ensure that neither the potentiometer nor the extension wire will change the EMF of the circuit as long as two connecting junctions at the potentiometer and two in the ice bath experience no temperature difference. This is absolutely yes. The provisions for a reference junction should provide a temperature that is accurately known, stable and reproducible. This one, okay, this one. a very common reference junction temperature is provided by the ice point, which is why, because it is 0 degree, because of the easy with which it can be obtained. So that is why, the reason why we use the ice bath for the reference, because it's easier with which can be obtained, which is 0 degrees Celsius. Okay. The electronic generally rely on the thermistor to determine the reference junction temperature as shown below. So the figures 13 basic thermistor circuit for a thermocouple. Okay, uncertainty for the reference junction are on under plus minus 0.1 degrees C, with plus minus 0.5 degrees C as a typical. And this is the benchmark for the industry to design their thermistor. Okay, in their system lah, in their device lah. Okay. Okay, now we talk about a standard. Okay, untuk thermocouple juga ada standard yang perlu dipatuhi oleh mana-mana distributor ataupun mana-mana creator for the thermocouple. Okay, the standard is follow the National Institute of Standard of Technology, or we call as NIST, provide a specification for the materials and a construction of standard thermocouple circuit for a temperature measurement. And table 2 shows the later designation and the polarity of the common thermocouple, okay, along with some basic application information for each type. The choice of the type of thermocouple depends on the temperature range. You can see they have a different application with respect to the different temperature range measured, the particular application, and the desired uncertainty level. Okay, you can see from the next slide, they have the uncertainty level for different type of the material. So you can see from here, there's a different percentage on that. So if you want to make sure that your device have a very accurate measurement, you need to make sure your uncertainty is less than what you expect. Okay. Table 3 provide the standard composition of a thermocouple material along with standard limit of error for the various material combination. Different combination of the metals will respect to the different value of the uncertainty. This limit specifies the unexpected maximum error resulting from the thermocouple material. If you have your maximum error is high, so something you need to do in terms of the collaboration of the materials, or you need to change the circuit, alright, because they have a lot of steps in order to design the step for the thermocouple. Okay. The NIST use a high purity material to establish the standard value of voltage output for a thermocouple composed of two specific materials. This results in standard table or equation used to determine the measured temperature for a measured value of EMF. And after they do their job, then they come out with the standard table yang kita refer over the world, which is the different changes of the temperature with respect to the value of the EMF. Nanti kita akan tengok table yang mereka keluarkan. An example of such table is provided in table 4 for the iron consistent combinable. This is the table that I mentioned to you before. Refer to the J-type thermocouple. And table 5 provide the corresponding polynomial equation that relate to EMF and temperature for the standard thermocouple. Okay, untuk persediaan final, saya recommend kamu untuk faham macam mana nak capture, macam mana nak ambil value yang, macam mana nak baca table ini, kerana ia akan disoal dalam soalan final. Okey, kita akan pergi pada example in order to get more information, more understanding on that. So this is how the table 4, which represent the difference of the temperature in a different reference temperature respect to the value of the EMF. Okay, and this is the table 4 is about. Okay, the table 5 is about. Okay, for the different thermocouple type, they have their range, a different range, yeah, of course. And then for that also, they have a different constant. If you see from this equation, C1 here, Ci here is representing different value of the constant. Okay, so it's related for depends on your application what for. Okay. Okay, now kita pergi kepada exercise in order to get more understanding. The thermocouple circuit shown in figures above is used to measure the temperature T1. Okay, understand. The thermocouple reference junction here, level 2, okay, at the temperature of 0 degree, of course, because it's in the ice bath. Okay, maintained by us. Okay, the voltage output is measured using the potentiometer. Okay, found 9.669 megavolt. Okay, correct. So what is T1? Okay, how you want to solve this kind of problem? Okay, back to the table that I mentioned to you. Okay, so from here they given to you the EMF is 9.669. Okay. Okay, they are given to you. So when you refer at the table that I mentioned to you before, 9.669 is at 180 degrees C, right? So straightforward, just you need to refer the reference temperature. You need to make sure you are in the correct reference temperature. So it is correct, it's 0. So you look at the EMF appear, which is 9.669. So directly you will get the temperature corresponding to the output voltage is 180 degrees C. It's a very basic and it's a very fundamental for you to understand the table, how you want to read the table. Okay, we go further. Okay, suppose the thermocouple circuit now has a junction 2 maintain at a temperature of 30 and produce an output voltage 8.132 megavolt. What temperature is sensed by the measuring junction? Okay, so for the solution, by the law of intermediate temperature, and remember what is the law of intermediate temperature is about? The output EMF for a thermocouple circuit having two junction. Now we have a two junction because they create a junction 2 there. So one at 0 C and the other at a T1. Thus, dia punya general equation dia become like this. EMF 0 to 30, EMF 30 to T1. So in overall, we get the EMF 0 to T1. Okay, so now EMF 0.30 is based on the table. Okay, you need to look at the table. Okay, 0, 30. So the value is 1.537. So you can get directly. However, for the EMF 30 T1, you already given from the slide. The given from the equation here. Okay, 30 is 8.132. So you just substitute it. Okay, you just plus it. You will get your value is 9.669 megavolt. Okay, millivolt. Okay, so from that 9.669, the equation is asking you about the temperature, right? What's the temperature? So you look back to the table. So 9.669 is at 180. So therefore, the temperature is sensed by the measuring junction is 180 degrees C. So this is the bagaimana dia bermain dengan table. So you need to understand, you need to know how to get the value for temperature and for EMF. Okay. There has a more example for that. Okay, we will go further. Just to remind you guys, this type of question will be similar to your final exam questions. Okay, we go to the more example. An iron contestant thermocouple is connected to the potentiometer whose terminal are at the 25 degrees C. Okay, understand. The potentiometer reading is 3.59 megavolt. Understand. What is the temperature of the thermocouple junction? Okay, they're asking you the thermocouple, the temperature in the thermocouple junction, the reference junction there. So the thermocouple potential corresponding to 25 degrees C is obtained from the table above. So from here, the 25 here, you will get the iron contestant is about 1.277. Alright, 1.277. This is 25, not 75. Okay, so from that, the EMF of the thermocouple based on zero reference temperature is thus. So you have your 3.59, you plus with 1.277, so you will get the totals of your reference temperature is about 4.867 millivolts. So by referring to this value, refer back to the table given, so you will get your value for your temperature is about 92.5. 4.8 is about here. So I think you know how to interpolate that, right? Because the value is in the middle of here, so you know how to interpolate that. If you don't know about, if you tak tahu bagaimana nak interpolate that, try to WhatsApp me, then we will discuss it more later. Okay, just interpolate as usual, so you will get your temperature will be 92.5 degree. I recommend you to do yourself at home, and please get this kind of result, this kind of question answer. Okay. Okay, sekarang ni kita nak masuk kepada multiple junction. Apabila tadi kita ada dua reference junction. Bagaimana pula kalau kita ada multiple of the reference junction in a thermocouple circuit? What's the advantage of that? So, more than two junction can be employed in the thermocouple circuit and can be devised to measure a temperature difference, average temperature, and to amplify the output voltage for a thermocouple circuit. Okay, as refer to the figures 14 here, you can see they have a 4 different reference junction in the circuit, right? Thermopile, we call as a thermopile. Thermopile used to describe a multiple junction thermocouple circuit that is designed to amplify the output of the circuit. So in your mind, you must remember, if they are mentioned to the multiple junction of thermocouple, thermocouple change the name into a thermopile. Okay, the average output voltage correspond to the average temperature level sensed by the N junction here, right? It's up to you, whatever numbers you want here, they will act. Okay, the thermopiles are particularly used for reducing uncertainty. So that is the advantage of the thermopile, for reducing the uncertainty in measuring small temperature difference between the measuring and a reference junction. So that is the advantage using the thermopile. Okay, kita sambung. A thermocouple range sense a temperature difference for the figures 15. A series arrangement designed to measure the average temperature difference between junction, and also used to measure deviation from a uniform temperature and the heat flux through a solid. Okay, so that is the advantage of the thermopile. Okay, and this is the different arrangement of the circuit with respect to the reference junction here. The parallel arrangement need ikut parallel arrangement of the thermocouple for sensing the average temperature of the measuring junction. So by looking at this circuit, we can calculate for the mean of the EMF. Okay, by using this kind of formula, and for temperature also you can calculate for the mean by using this type of formula. So this is the general knowledge for you guys to understand about this subtopic. Okay, so now we go to the second last subtopic in this topic, which is about the radiative temperature measurement. So kita nak tengok kalau kita ada kita punya principle tu, kalau ada sumber radiation untuk detect the temperature measurement. Okay, radiation refer to the emission of electromagnetic wave from the surface of an object. Understand, this radiation has characteristic of both wave and a particle, which lead to the description of the radiation as being composed of photon. This is a physics term. The photon generally travel in straight line from a point of emission to another surface where they are observed, reflected, and transmitted. The electromagnetic radiation exists over a large range of wavelengths that include the X-ray, ultraviolet radiation, visible light, and thermal radiation. Okay, like this figure 17 is about. So different wavelength will create a different different spectrum in the electromagnet. The sensor for a thermal radiation need not be in contact with the surface to be measured, making this method attractive for a wide variety of application. So this type of principle used by the sensor of temperature sensor camera that available in the airport, for example, right? So no need get a contact between the object and also the device, but is make a very accurate result achieved on that. So that make this method attractive for wide variety of application. The thermal radiation emitted from the object is related to its temperature and has the wavelength ranging from 10 to the power -7 and 10 to the power -3. If you mention here is about around the here, yeah, the thermal radiation acting on that. Okay. So the radiation emitted by an object is proportional to the fourth power of its temperature, which represent the general form of EB. EB is the flux of energy radiation for the ideal surface, or we call as a black body emissive power, is equal to the sigma T quasar pi. Okay, the Max Planck developed the basis for the theory of quantum mechanics as a result of examining the wavelength distribution radiation. I think you pernah tengok this kind of equation dalam fizik masa secondary school, kan? Dalam di matrix juga ada explain benda ini. So saya just straightforward. So this is I think you are quite familiar with the electromagnetic spectrum here. So figure 17 shows the electromagnetic radiation exists of a large range of the wavelength. So you can see the wavelength is increased. The increase also increase also the capability of the spectrum. Okay, either is in X-ray, ultraviolet radiation, or maybe it's invisible light. We have 7 colors there, and infrared or a thermal radiation. We look at this kind of spectrum in this analysis. Okay, the maximum energy emission shift to a shorter wavelength at the higher temperature. By referring to the Planck distribution in figures 18 here, you can see when the wavelength, the maximum energy, this is the maximum energy, okay, this is maximum power, emission shift to a shorter wavelength. So when the wavelength is short, so it will create a higher power, higher energy emission with respect to the higher temperature. Okay, that is the figures is talked about. Okay, so we go to the radiation detector. The first technique involves a thermal detector in which observe radiative energy, elevate the detector temperature as shown in figures 19. Okay, from here this is the schematic diagram for the basic radiometer. So this is lens, this is a focusing mirror, this is a focusing mirror, and 3 is the detector. Either you use a thermopile or thermistor. Thermopile detector provide a thermoelectric power resulting from a change in a temperature. The thermistor is used for a change in resistance with temperature. Understand? A second basic type of detector relies on interaction of photon with the electron, resulting in the electric circuit. In the photomultiplier tube, the emitted electrons are accelerated and used to create an amplifier current, which is measured. The photovoltaic cell employed as a radiation detector. The photovoltaic effect results from the generation of a potential across a positive-negative junction in a semiconductor when it is subject to the flux of photon. Don't worry about the theory here, because this is just about the theory of how it's work for the radiation detector. So just for your knowledge, in order to understand the detector using the radiation. Okay, so we go to the radiative temperature measurement. So kita tengok, kita ada beberapa jenis radiator untuk mengukur pengukuran suhu. Yang pertama adalah radiometer. Radiometer is measure a source of temperature by measuring the voltage output from a thermopile detector. Oh, dia pakai thermopile and dia measure the voltage. Okay, good. The increase in temperature of the thermopile is a direct indication of the temperature of the radiation sources. In the industrial side, it's widely used for the automotive application. Oh, dia digunakan pada kereta-kereta kita yang kita guna tu banyakkannya menggunakan radiometer. Oh, I see. And pyrometer, optical pyrometer identify the temperature of the surface by its color and more precisely the color of the radiation it emits. Okay, a standard lamp is calibrated so that the current flow through its filament is controlled and calibrated in terms of filament temperature. So pyrometer ni banyak bermain pada surface menggunakan color yang berbeza-beza. Okay, different color will give you a different signal on that. Okay. So this is the example for the radiometer, okay, industrial infrared IR thermopile sensor with a different component inside that. So this is a schematic diagram for displaying a filament optical pyrometer. So from here, this is our observation. So this is how the arrangement of the lens inside the circuit. So the last but not least, we have our optical fiber thermometer. Okay, the thermometer, the temperature sensor in this system is a thin single crystal aluminum oxide, where it is here, which is in number 3 here. Okay, a metallic coating on the tip of the fiber foam, which is here. A black body radiating cavity which radiates directly along the sphere crystal fiber. Okay, the operating range of this temperature is 300 degrees C to 1900 degrees C. It's not bad. Signal transmission is accomplished using a standard low temperature fiber optic. A specific wavelength band of the transmitted radiation is detected and measured, and these raw data are reduced to yield the temperature of the black body sensor. And this is how the optical fiber thermometer looks like. They have a 3 different section here. The outside we have our protective coating, the aluminum oxide. They got the the iridium field inside the component, and also the another section here, they have the sapphire wire, which is the crystal fiber inside that. Okay. Okay, this is just the example of the application using the infrared thermographic image. This is flare. This is temperature detector is available in our department. Okay, you can check at the lab. Okay, so this is how they capture the contour of the temperature of the object. Okay, I think we go to the last subtopic. Okay, which is the error in a temperature measurement. Okay. Okay, this is the last section for this topic, and then we finish. Okay. In general, these two type of error in a temperature measurement. They have two type of error. The major error in a temperature measurement. Sorry, they have a wrong spelling here. Okay, the first one, error is due to the uncertain information about the temperature of the sensor error itself. Come from random interpolation error, calibration bias error, or other type of error. Okay, and the second one is we call as insertion error. A temperature probe indicates a different temperature due to a physical mechanism such as conduction, radiation, or recovery error. The temperature reading could be substantially different from a true temperature. So from here you can see the difference between the errors that happen in the temperature measurement. So we go further on that. So kita pergi tengok a conduction error. What is a conduction error? Also called as an immersion error. Okay. This error neglect the radiation error. Oh, okay. And happen when we want to measure a plate or object, and the probe must pass through some environment with a different temperature. Oh, okay, I see. If the plate temperature is higher, okay, this is how the diagram looks like. Okay, If the plate temperature is higher than the conversion environment, heat will be conducted out along the probe, okay, into the converting environment, and the temperature reported will be lower than the true plate temperature. This is energy conducted along the element and transferred by the convection for the surface, okay. And this is how they calculated for they have the relation between the temperature also, okay. Enhancement can be made through the improvement of the probe design. This is how they can improve the error on that, okay. So example for insertion error, okay, due to the radiation. Kalau tadi kita pakai conduction, dia ignore the effect of the radiation. For the insertion, there is due to the radiation. In presence of a significant radiation heat transfer, equilibrium temperature of a temperature probe may be different than in fluid bending method, okay. Okay, and also the neglect transfer by conduction, yes, of course, because due to radiation. At a steady state condition, convection heat transfer is equal to the radiative heat transfer. For the convection is equal to radiation is equal to 0. So this is how they set up the conditions for the for the calculation. So where this is the general form of that. So H is the convection heat transfer, and A is the surface area of the thermometer, and sigma here is present the Stefan-Boltzmann coefficient, and strain here surface emissivity of the thermometer. Tp here is the temperature reported by the probe, and T infinity Tg is the true gas temperature. Okay. So now we go to the radiation shielding, analog to insulation. Opaque surface interposed between temperature sensor and its radiative surrounding to reduce the electromagnetic wave interchange. So this is how they calculate for the radiation shielding. So Fs here is the radiation view factor. Alright, this is F here, the radiation view factor. So this is how they calculated, which involve the surface area of shield and emissivity of the shield. This is just for the knowledge or for you. Don't worry about that. It's not be covered in the final exam. Okay. So we go to the example. You can go through on the example, and then you can see how they get the solution for the soalan. I just go through fast on that. So improve with the radiation shield. A shield having the emissivity of 0.1 is placed around a thermometer. In example 8.12, such that the area ratio is 0.3. Okay, the temperature is indicated by the thermometer under this condition is 5%. The convection heat transfer coefficient is assumed to be the same. Okay. Also, this is what how they calculated for that. This is one of the example. Also, you can go through on that. So you will see the result is about how they calculated for that. So I go to the summary for you guys to understand. So in the summary, you have your random error, you have your systematic error. Okay, so you can see the different for every errors there they are stated in here. So when you have your system, so you need to check either your system have uncertainty or not. With the uncertainty, you can see the type of the error of your system, of your circuit. Alright, with different applications on that. Okay, in this subtopic we just cover some of that. We not cover all. Just for your for your understanding, for your knowledge. Okay, so I think that's all for this topic. Thank you very much. You still have one topic with me, which is about stress strain measurement. Okay, thank you very much. Take care. Assalamualaikum.